Okay, hi, Year 12 Extension 2. We're going to look at the next topic, which is proof by further mathematical induction. Now typically in mathematical induction, the cases usually start with n equals 1, and then you've got to prove a truth for n equals 2 and so on. We're going to look at some examples where the first case is not n equals 1, it might be n equals 2 or something else. So let's have a look at our first question up here. We've got to use mathematical induction to show that n squared plus 2n is a multiple of 8 for all n, an element of the natural numbers, where n is even. Now natural numbers, 1, 2, 3, 4, 5, they're all the counting numbers you would have learned in primary school, so natural numbers just means like your normal numbers, not including 0. So we'll start off by looking at the first case. Now it says n is even, so you're not going to try n equals 1, you need the first even number. So let n equals 2. Therefore, n squared plus 2n is equal to 2 squared plus 2 times n, which equals 8. Alright? And that's a multiple of 8. Okay? Therefore, true for n equals 2. Okay? So it works for n equals 2. Well, the next case. Alright, now, because n is even, we've got to look at the next even number. So we're going to start with our supposition. So suppose n squared plus 2n is equal to, suppose true for n equals k, where k is even. Okay, k is an even number. So that means, therefore, suppose k squared plus 2k is equal to 8p, and when p is an element of the natural numbers, okay? So supposing it's true for n equals k, where k is even. Alright, then we've got to prove true for n equals, now it's not k plus 1, because if n is even, k plus 1 will give you an odd number, so it's got to be k plus 2. Alright, so k plus 2. So prove true for n equals k plus 2. Therefore, required to prove that k plus 2 all squared plus 2 outside of k plus 2 is equal to 8q, right, where q is an element of the natural numbers. Alright, now with these you have to start with the left hand side, of course. Left hand side equals k squared plus 4k plus 4 plus 2k plus 4. Now, you've got to figure out where you're going to put your assumption. Now, I need a k squared and I need a 2k, so I'll put those together. So that gives me k squared plus 2k, then I've got plus 4k plus 8, before in the full make the 8 there. Okay, now I can use my assumption here, that's 8p plus, so this here gets replaced with 8b, plus 4k plus 8, and we should put it down from assumption. Okay, now I've got to show this is equal to 8q, where q is a natural number. So what I could do is, this is one way of saying it, I could write down 8p plus, I'm going to put down 1 there, and then for the 4k I'm going to put down k on 2. Now, k is even, isn't it? So if k is even, k divided by 2 will be a natural number. So I'll put down but k on 2 is an element of the natural numbers since k is even. Okay, k is an even number. So k on 2 will be an element of the natural numbers. So if that is a natural number, p plus 1 plus k on 2 will also be a natural number. So what I can say then is therefore left hand side is equal to 8q, where q equals p plus 1 plus k on 2, and q is an element of the natural numbers. Okay? Then you've got to put your conclusion down. You're going to write down, alright, therefore true for n equals k plus 2 if true for n equals k. Since true for n equals 2, n squared plus 2n is a multiple of 8 for n, or actually for all n element of the natural numbers, n even. Okay? There we go. So that's the first example. Make sure you've copied all that down. You might want to copy that down and have a go at the question again yourself. Alright, let's have a look at another question. Number 2. Okay, question number 2. Actually, before we do that, here, when you got to this part here, you could have done it a different way. You could have said k is even, therefore let k equal 2a. A is an element of the natural numbers. Yep. Therefore left hand side equals 8p plus 8a plus 8, which equals 8 outside of p plus a plus 1, right, which equals 8q, and so on. Okay, so you could have done it like that as well. I just did it this way so I didn't have to introduce another variable, but it doesn't matter, you can do it that way if you want to. Let's look at the second example. I'll just write that out. Question number 2. Here we go. Use mathematical induction, lowercase there, induction, okay, to show that 3 to the n plus 2 to the n is divisible by 5 for all natural numbers, for all n element of the natural numbers, and where n is odd. Okay. Now I'm just going to use the notation from the textbook here so you get to see different ways of writing out the notation. So we'll start off by saying let P of n be the proposition. P of n be the proposition that 3 to the n plus 2 to the n is equal to 5b, all n element of the natural numbers, n is odd and b is an element of the natural numbers. Okay, so Pn is proposition for n. Alright, so firstly, we're going to look at P of 1. So P of 1 will be 3 to the 1 plus 2 to the 1, which equals 5, which is a multiple of 5. Therefore, P of 1 is true. Okay, good. Alright, next. So P of 1 is proposition for n equals 1. Alright, now, next part. We're going to assume P of k is true. Therefore, assume 3 to the k plus 2 to the k equals 5p, right, where p is an element of the natural numbers and k is odd. Okay, so there's our assumption. Then we've got to prove true for p of k plus 1. Actually, not for p of k plus 1, that's not true. We've got to prove p of k. Now, k is odd. If I go k plus 1, I get an even number. The next odd number should be plus 2. So prove p of k plus 2 is true. Right? So that means required to prove that 3 to the k plus 2 plus 2 to the k plus 2 is equal to 5q. Q is an element of the natural numbers. Okay. Alright, so we're going to start off with the left-hand side, aren't we? So left-hand side equals 3 to the k plus 2 plus 2 to the k plus 2. Okay, now, I've got to use my assumption in there somewhere, so I need to get a 3 to the k and a 2 to the k in there. So that's what I'm going to do. I'm going to split this up. So I'm going to have 3 squared multiplied by 3 to the k plus 2 squared multiplied by 2 to the k. Okay, now, looking good so far. Now, for my assumption, I can manipulate the assumption. So here, I could change this to 3 to the k equals 5p minus 2 to the k. Right, so I can use this as my assumption instead. So I can just substitute in for 3 to the k. So I'm going to get 9 brackets 5p minus 2 to the k plus 4 times 2 to the k. Okay, so that gives me 45p minus 9 times 2 to the k plus 4 times 2 to the k. Alright. So 45p. Now minus 9 plus 4 is minus 5 lots of 2 to the k. And that is equal to, now obviously we can take up 5 and then 9 minus 2 to the k, which equals 5q, where q is equal to 9 minus 2 to the k, and q is an element of the natural numbers. Okay. Now, so we proved, well, that's obviously a multiple of 5. So using that notation, we would say therefore p of k plus 2 is true if p of k is true. Okay? but P of 1 is true. Therefore, P of n is true for all, P is true by mathematical induction. So, if you manipulate the assumption there, that just becomes quite an easy substitution and not too bad. Alright? Now, questions you can do, I'll put them up here. I want you to do 502 from the textbook. Now, the reason we're starting on 502 is 501 is just a revision of the extension 1 mathematical induction. You're welcome to do 501 as well, but we're just going to stick to the extension 2 content starting from 502 from your textbook. Okay, that's it.